There's a lighting problem in Gordon's book, in the Gordon text, on page 244 that I want to illustrate about lighting calculation. And it is, we'll talk it out and then I'll draw it. I'll explain. I don't know if we use this book or not. Calculate the average maintained the luminance work plane of a 15 by 30 foot office with an 8-foot ceiling. So 15 feet by 30. Ceiling at 8.6. And there are a regular arrangement of 8 luminaires. So each luminaire has two 26-watt triple tube compact fluorescent lamps. So what does that mean? There are 2 lamps in each light, right? So what's a regular arrangement of 8 luminaires? Well, it's got to be 1, 2, 3, 4, 5, 6, 7, 8, right? That makes sense? You're going to have more along the long edge of the room. So if we were to divide the room in the center, there's 15 feet on each side, right? Center again, 8.5 feet. So these are going to be, I think they're going to be 8.5 feet apart, because there'll be 8.5, yeah. So these are at 8.5 in that direction. Then in this direction, we have the same thing, right? Center line through here. Will give you 8.5 feet on each side, so that the spacing of the lights here is 8.5 feet. So that's your, you got to lay out the problem first. You have lights at 8.5 foot centers in both directions. From the lamp catalog, all right, number of lamps, 2 lamps per luminaire. That's 1. 2 is 2 lamps per luminaire, 2 CFLs. At 1800 lumens each. So I'm just reading from the problem. I guess you can barely see that. Damn lack of a camera here. 3. Let me start with the calculation itself, which is given in before this begins, is the total illumination in foot candles is the number of lamps times lumens per lamp, right? Times the light loss factor times the coefficient of utilization. What's the coefficient? We'll talk about that. Divided by the area. So that's going to give you the average illuminance. This is what we're trying to get. Right? 3. how do we get the light loss factor? It is the light loss depreciation times the lumen, it's a dirt depreciation factor called LDD. And then they have a component called, I think the BF stands for ballast factor. So all these things are parts of the component of the fixture that contribute in a positive or negative way, usually in a negative way, to the amount of light that that fixture can generate. How are we doing on time? 6 minutes. I don't know how we finally get through here. A, B, C, and D are telling you that to look up in tables in the appendix, fluorescent compact fluorescent has an LLD of 0.85. So there's some light loss by virtue of that, the nature of the fixture. That's A. B, the dirt depreciation factor for that is going to be 0.96. A little bit less. That's the LDD. The ballast factor, again referring to manufacturer, is going to be 1. So that doesn't change anything, right? These are all coefficients. Coefficients are multipliers, so they modulate a particular result. And then finally, the light loss factor is the product of all of these, right? It's that times that times that. A times B times C. So here we get 0.85 times 0.96 times 1 equals 0.82. That's going to be that number. We have the lumens. That's 1800 per lamp. But there are 2 lamps in each fixture, so the number of lamps is going to be 8. Is the number of fixtures times 2. There's going to be 16 lamps. 16 times 1800. Our light loss factor is 0.82. And now this brings us to an important number called the coefficient of utilization. And this is where you figure in the environment, technically. There are tables that are published for certain reflectance values for the ceiling, walls, and floor. And the floor is typically set at 20%, and that doesn't vary. You have to look for tables that set different values to floor because it doesn't contribute all that much. So the first thing we have to do is find, now number 4. Remember, we're looking for now to find a coefficient of utilization. CU. We need the room cavity ratio. Room cavity ratio, 1, or A. RCR, room cavity ratio. is 5 times the height times the length plus the width, The height being the distance of the lamp, the source of light, to the surface. So think of this room in section 15 feet, right? And we have a tabletop. Work surfaces are typically 30 inches above the ground, or that's 2 feet, 2'6". So the ceiling elevation is 8'6". So H equals 8'6" minus 2'6". H is going to be 6 feet, right? There's your light, any representative light. This is a section, cross section, right? Because the shorts, it doesn't matter which side. 5 times that height is going to be 6. The length and width of the room over the length times the width of the room. So it's the sum over the factor. So that's going to be 5 times 6. Remember, we're in feet. We're talking about foot candles, feet. So everything is in units of feet. 5 times 6 is the height. Length of the room, 30 plus 15 over the length times the width of the room. Five times 6 is 30. These cancel out. So it's going to be 30 plus 15, 45 over 15. Which is 3, I think, right? Does that make sense? This is your room cavity ratio. If you can do a single problem like this, you can do any number of them, all right? This is really, okay. Now, table 14. I'm going to repeat what I said before. There are published tables that have reflectance values for ceiling, walls, and floor, and the floors are typically pegged at 20%. I'm going to look up a table and then kind of replicate here. Table. We're looking for 80% ceiling reflectance, 50% wall reflectance. And this is what I mean by environment. You determine this, right? You're painting the walls or applying finishes to the walls or otherwise. And the 20% is invariably what we attribute to floor reflectance, right?